Sorry? Okay. Yeah, so I can thank again the organizers. Yeah. Yeah. We can continue this. Okay, yeah, so yeah, despite what my badge says, I've just recently moved to NICAP actually, so I'm now in Amsterdam, but I was previously part of N3S, and with that affiliation, I've done most of the work I'll be talking about as well. And yeah, I just wanted to also apologize that, okay, maybe this topic is not directly related to astrophysics, but there are connections, of course, to cosmology, for instance, leptogenesis and such. So I still hope that you might enjoy some of this. But before I delve into my topic, lepton number violation, I have one question for you, mainly for the senior people who remember every single paper. Like, what is this showing? Like, what are these guys discussing? Like, yeah. So this is here in the corridor, right, at GGI, and I've been thinking about this. Yeah. Like, can you think of like what kind of topic they're discussing? And like, is this actually a good idea to show this kind of picture on the wall if you want to attract like funding? And I don't know. Well, like, okay, let's continue. Okay, so lepton number violation. So okay, so that's, as Andrea said. Okay, he was not talking about lepton number violation, but clearly that's something, that's a concept that is tightly related to neutrino masses, right? And if they are Majorana, then lepton number would be violated at some level. And within the standard model, as such, what we know that exists, that non-perturbative dynamics, we have B plus L number violation, but B minus L, the orthogonal sort of combination of a baryon and lepton number, seem to be conserved, and it looks like it is a non-anomalous global symmetry of the standard model. And you may say it's accidental, but that's a question, right? It could be a relic, so it's not that difficult to imagine that this symmetry is actually restored at some high energy and can be maybe even gauged, right? And the reason why we don't observe any lepton number violating processes at low energies is simply that all these effects are maybe suppressed then by the hierarchy between the standard model physics and the new physics. So simply all these processes are come with some 1 over lambda, where lambda is the scale of the new physics, and if it's high, then the effects are small. Okay, so yeah, Andreas talked a lot about distinguishing between Dirac and Majorana masses or neutrinos, right? So I'll be mostly focusing on this case, and I'll be focusing on like the ways we can actually probe lepton number violation. Of course, to probe new physics, okay, the problem is here. There is a plethora of new models that introduce Majorana masses for neutrinos, right? And so, what's the best way how to approach them all in single framework? I'll argue it's the effective field theory, because that provides a robust and model-independent approach, really. And even the standard model you can view as some kind of an effective field theory, right? That's low energies, assuming that the new physics is well above the electroweak scale, right? If there are degrees of freedom that are possibly lighter, that can be the need to include them in your effective field theoretical description. But in principle, you can still use this framework. Or alternatively, if you want to avoid some limitations of EFT and study, for instance, resonant production at gliders or so, maybe something like simplified models is a good alternative. Lepton number violation in the standard model effective field theory, right? So if you take the particle content of the model and you construct all operators that are invariant under Lorentz symmetry and under the standard model gauge symmetries, then you get these higher dimensional operators, right, that you can add to your Lagrangian that are always suppressed by the corresponding power of the high energy physics scale, or the typical scale of the effective operator. And so we know that interestingly, it can be shown that Lepton number violation appears, or Lepton number by 2 units appears only at odd dimensions in the series. And at dimension 5, as you all know, I'm sure, there's this unique Weinberg, right? Just LLHH. And dimension 7, we have more of them, actually 12. It took some time to come up with the basis. So we know basis only about 8 or 10 years. And also then, of course, the next dimension is dimension 9, which is still interesting for also what I will be talking about for neutrinos double beta decay, because that's actually the natural mass dimension at which neutrinos double beta decay appears, because you have 6 fermions, right? And then, yeah, the way you can understand this is that, okay, these heavy degrees of freedom that live maybe at high energies, right? So for instance, if you have some kind of Laprise symmetric model or something like that, they can be integrated out, and at low energies, they exactly trigger these effective operators. Okay, as Andre already mentioned, the best way to search for Lepton number violation turns out to be to search for double beta decay, mainly for its neutrino-less contribution, right? So for neutrino-less double beta decay, so there is in the standard model 2 neutrino double beta decay, which is just like single beta decay squared kind of, but it's simply for some nuclei preferable to transition via this kind of process. So simultaneous transition of 2 neutrons to 2 protons and emission of 2 electrons to antineutrinos. And then not that difficult to imagine that, okay, if neutrinos are Majorana, you can actually change the neutrino between the 2 beta decaying vertices, right? And so then this process violates Lepton number, because you start with a nucleus and end up with daughter nucleus and 2 electrons. So you have 0 leptons in the initial state, 2 leptons in the final state. Yeah, Lepton number has been violated by 2 units. And yeah, there is a number of experiments that are actually searching for this process in different isotopes. The best limits come from xenon. And these experiments have already observed the 2 decay. The rates there are around 10 to the 20 years. It's one of the rarest decays or processes I'll ever observed. And okay, the limits on the neutrino-less version of this process are around 10 to the 26 years, right? So this is the standard picture, let's say, but okay, you need of course to go beyond the standard model to be able to draw this kind of diagram. So you need the insertion of this light Majorana neutrino mass, right? So that's what's called the standard mechanism, or maybe rather light neutrino exchange mechanism. And so simply if the light active neutrinos are Majorana and have Majorana mass, then you can draw this. And then the decay rate for this kind of process would be proportional to this effective neutrino mass that is projected out like this. So it's this kind of weighted combination of the neutrino masses, right? Where these are, of course, the entries from the first row of PMNS matrix. Those are the weights here. And and then it depends on the outgoing leptons, the electrons, right? So that's the phase space. That's kind of easy to calculate. And then the difficult part is, of course, this nuclear matrix element. That's the many-body physics. For that, you need to use your favorite nuclear structure model and then calculate the nuclear matrix elements. And if you're able to do that, then you can translate the bounds on the half-life or decay rate into the bounds on this effective neutrino mass, right? And then you can plot this effective neutrino mass in this kind of diagram in dependence on the absolute neutrino mass scale. Possibly, if you plot it in dependence on the sum of neutrino masses, modulo many caveats, of course, you can maybe constrain this plot from the right from cosmology and top down from neutrino double beta decay. And that depends, of course, on the ordering, inverted versus normal. There is this unfortunate thing that, okay, it may happen that nature is really not nice. And in the normal ordering case, it can happen that the parameters conspire in such a way that maybe there is Lepton number violation in nature, but we wouldn't see neutrino double beta decay because this M beta beta can actually vanish. but as you can see, it's actually unlikely. And also, always you should remember that this plot reflects only this one contribution. While if you have some kind of a UV model, this would hardly be the only contribution that would contribute to neutrino double beta decay. And the additional contribution don't need to be necessarily negligible. There are interference terms, etc., etc. So yeah, this is you can draw like these four other contributions, four other diagrams that the first one is proportional to the heavy mass, the right-handed neutrino mass, doubly charged scalar and its interaction with the right-handed H bosons, and so on. And for lepton quarks also, you can draw these diagrams. You can take something like R parity violating SUSY, where you have many free parameters, so you can even play even more with that. You have the diagrams with neutralinos, etc. In all these cases, however, and that's what was already mentioned, right? Is this kind of black box theorem? You would always at some loop level generate Majorana neutrino mass, even though this particular contribution would be really tiny and would be pretty negligible. Yeah. So since we have so many models, yeah, I would again just like I already mentioned the EFT, so that's also a good way to approach the so I mentioned that in SMEFT, right, and standard model EFT, you have lepton number violation at the odd dimensions. So these operators can contribute by a to neutrino double beta decay. So there is a lot of literature that where this has been discussed, of course. I also contributed to it a bit. And if you're again able for these exotic modes calculated to the phase space and the nuclear matrix elements, then you can in principle constrain the particle physics, which is incorporated in this, or represented by the Wilson coefficient here, which is just the coupling that's associated with each of these effective operators, right? So the Lagrangians looked at low energy, for instance. And then, okay, once you constrain the Wilson coefficients, you can employ these constraints and you can take any model that you prefer, match it onto the EFT, and get constraints on the parameters of your model, right? So that can be a fairly involved procedure. So what we've done, we've collected that has been published in the literature over last years, and mainly Oliver Scholler, who is a PhD student in Heidelberg. He coded up basically this Python tool, this Python package, NuDope, that incorporates this whole complicated of EFTs, right, which includes RG running and matching. So you start at your preferred UV scale, and yeah, if the only thing that you need to input is if you have your favorite model, right, you need to match it onto the standard model effective field, right? And then what the code does, it spits out the half-life for neutrinos double beta decay in your model. It has many plotting functions, etc. It incorporates different sets of nuclear matrix elements, phase space factors, low energy constants, or nuclear form factors. These are to some extent equivalent, right? So you can access it online where you can play with it, but if you want to do probably anything serious, you want to download the package and just use it. This is how the online tool looks like. So you can, for instance, you can define a model. You define a model, then you select what kind of, I don't know, nuclear matrix elements you want. So let's say SM is shell model here. So you choose shell model, and now you choose where you want to start, whether at the high energy, so at SMEFT level or left level, and here you can then put in the numbers for the Wilson coefficients, and it tells you half-life is. It can give you also the formula for the half-life in LaTeX and so on. And then you can plot the angular distribution or the single electron energy spectrum and the other things. Okay. Yes. No. Those are just inputs as numbers, and then you use your own numbers if you like. That's good also. If you have, that's already available. Yeah, exactly. Yeah. What does it? This low actually use also the nuclear matrix elements, right? So in principle, you can do this. If you go over the literature, you can do it by hand. You can code it up yourself, but it's a lot of work and the quite so it should be. Yes, yeah, for the whole basis, up to dimension 9. Yeah. So then the question is, okay, like great. So we know we can have a lot of different contributions to this process, right? But if we actually see it, would we be able to tell these different contributions apart? Would we be able to say something about the underlying new physics that we are interested in? At least particle physicists, maybe. Well, there are some possibilities of distinguishing different neutrinos double beta decay mechanisms. Yeah, one of them is, for instance, to study the phase space observables, right? So electron energy spectra or the angular correlation. Another is maybe comparison with other double beta modes or processes and their neutrinoless modes, but that's hard because all the other processes are really heavily phase space suppressed. But what you can do, of course, is to compare ratios for different isotopes, right? Of course, the particle physics shouldn't depend on the isotope. So if you take a ratio of the half-lives, it drops out. And you can compare, in principle, the measured ratio of half-lives in two different isotopes with what you calculate the ratio of nuclear matrix elements and the phase space vectors, right? And in principle, if you get ratios that are distinct enough, then you could be able to tell different contributions apart. So that's what we thought about. That's what we applied to this master formula framework by Chirigliano et al. And there at the low energy T209 that can contribute. And turns out that using the phase space observables, you can distinguish 4 different groups of these operators, or just 4 different groups that have different that provide different phase space observables. And if you use the half-life ratios, then there are in principle 12 in principle distinguishable groups of operators. The main issue, however, is of course the nuclear uncertainties, right? And not just nuclear matrix elements, but also the unknown low energy constants, which are basically the Wilson coefficients at the chiral EFT level, which in many cases, okay, so this is what I mean. So let's say these are the nuclear matrix elements, right? And these are then combined in different contributions. They come with different coefficients, which are the low energy constants at low energy. Some of them are known, have been measured or calculated on lattice, but these exotic contributions to double beta decay contain a lot of unknown LECs for which we have no idea what they are. It could be in principle calculated, for instance, on lattice, but that would take a lot of time. So I don't think that will actually happen unless we see the process, unless we observe neutrino double beta decay, right? And the uncertainties from nuclear matrix elements are shown here, right? So different nuclear structure calculation. I won't go over these, but different nuclear structure calculation give you quite different results. I'm saying here the difference is factor of 2 or 3. Well, if you compare some latest results from the ab initio calculations, then it can be even more. It can be actually an order of magnitude. We compare those with some other more phenomenological calculations. They seem to be smaller in general, but the best model, or like the closest model from the older approaches, seem to be Shaw model. So yeah, so these are the limitations. I'll not spend too much time on this. So this is basically what we did. We looked at the ratios, and since we didn't have a number of these low energy constants, right, and then there are uncertainties on the nuclear matrix elements, we have to vary those, or we have to marginalize over those. And then if you look at the ratios of the half-lives, you get, instead of like one number, of course, you get quite a spread over the number. So it would be really difficult to tell individual operators apart, but maybe the hope would be that you would at least distinguish any exotic contribution beyond just M beta beta. But even that would be difficult, and there is like 1 or 2 operators that could be in principle distinguished if we are lucky and we look at the right isotopes. But it turns out that for instance, this right-handed vector current, dimension 6, has also can be also distinguished by the phase space. So maybe still the best thing that we can do is once we observe neutrinos double beta decay, right, is to design some experiment. Super NEMO, right, or NEMO 3 exists already, and now they have Super NEMO demonstrator, I think, that would be able to measure the energies of the electrons, so they can measure the single electron energy spectrum in principle. So the spectrum I'm showing here, right, these are spectra for these 4 different groups of operators, right? So this is how we can distinguish them either from the spectrum, or above the diagonal I'm showing the angular correlation of the 2 outgoing electrons, right? So from the geometry of this experiment, right, they can tell whether the electrons in the same direction or back to back, right? So that's the main thing that you would that could help you to distinguish the exotic contribution, the new physics contribution, let's say. Okay, so that's not, yeah, it would be really difficult to pin down, let's say, the particular effective operator or particular model from neutrinos double beta decay itself, and there are all these challenges. So the question is, are there some other probes of Lepton number violations? So we looked into that, and we went to, say, next to leading source of Lepton number violation, which is dimension 7. We took this basis of 12 dimension 7 delta L equals 2 SMEFT operators. So it's not a real EFT. This is what you can construct. There is no additional operator, and none of these operators is linearly dependent, or you cannot express any of them. So it's really a basis. We ask ourselves, okay, so where can we look for the effects in like laboratory experiments, and can we possibly probe these both at low and high energies? So clearly the limits from neutrinos double beta decay are the best, and that's what we expected. But there are these caveats with the nuclear uncertainties, and also it is double beta decay, right? So in reality, what you're probing is strictly speaking, it's just the electron flavor, right? If lepton number violation is dominantly produced or like appears dominantly in other flavor, you would miss it with neutrinos double beta decay. So I think still it makes sense to like look elsewhere, and that complementary probes are also vital then for potential distinguishing of the signal, right, if we see it. And so this is what we've done. We went through the literature, and in this paper we collected, expanded, updated the limits from these. For instance, you can study rare meson decays. So the best limits come from the NA2 experiment at CERN, from kaon decay, right? You can look at neutral current Lepton number violating NSIs at 7s, or harsh current Lepton number violating NSIs on baseline oscillations. In fact, there is some data from Minos and Kamland where they're sensitive to the lepton charge in the final state, and in principle, you would be able to, or you're able to constrain lepton number violation from there. There are also lepton violating tau decays, so that's interesting because that touches the tau flavor, but the limits are not great, honestly. There is non-standard decay that's quite interesting. There's one operator that is purely dimension 7, and that's constrained quite stringently by this. There is also the muon to positron conversion that Andre already mentioned, and they worked on it. And that's interesting, especially in light of the upcoming mu2e experiment, right? But the constraints are also not that great. On the other hand, this combines the muon and electron flavors, right? So that is interesting from that point of view. Neutrino magnetic moment can actually constrain quite stringently two operators, as I will show. And then another thing that we looked at, and that wasn't in the literature at all, is at least for these operators, is a search for Lepton number violation at colliders. So we derive limits from the LHC using this kind of for searching for this kind of processes, right, that are shown here. So you have to same sign dilepton plus digit and no missing energy, right? So this kind of process is the way to go, or that's what you want to see if you're searching for lepton number violation at colliders, and it's also model independent. Basically, if you think about it, it's nothing else than just the same diagram as for neutrinos double beta decay, right? You just rotate it a bit, and that's called Keown-Sinanovic process. And there was actually a search done by Atlas, so we recasted that and we followed the analysis that was done for the Weinberg operator, and we did that for the dimension 7 operators. Of course, there are some caveats, right? Now you're at high energy, so the momentum transfer is not necessarily small. So you need to be careful when using the effective field theory. But we are fairly conservative, I would say, and then still for some operators, such as this DULLD, for instance, we got quite interesting limit of 5 TeV. And then now in this setup, we are looking, or we are constraining muon flavor, right? So in principle, again, this constraint is new, and then this component, let's say this flavor component of these effective operators is not constrained by neutrinos double beta decay. And the limits would be even better if we have a future bigger collider. Okay, so it is a bird's eye view of all the constraints combined. So as I mentioned, the most stringent limits usually come from neutrinos double beta decay, but with the caveats. Well, on the other hand, there are operators at 3 level, at least, to neutrinos double beta decay, right? So then, for instance, the neutrino magnetic moment limits are interesting for this one particular operator, that the Keown limit is quite stringent. So that's from an A62. It's this kind of process, right? K plus 2 pi plus nu. So that's also great because you're probing all the flavors, because you don't know what these neutrinos can have any flavor. But the collider constraints for many or number of these operators, 5 or 6, turn out to be the second most stringent. And again, they constrain the muon flavor. And then you can, in principle, play all these kinds of games. And okay, you can imagine that if you see some discrepancies in one of these processes, it could be lepton number violation, right? And so if you see lepton number violation, let's say in neutrinos double beta decay and or in collider, then you can look for it elsewhere, and that could, in principle, tell you what is the dominant source, which operator may be the dominant source, and it can also help to disentangle maybe the flavor structure of the contribution. Okay, so let me conclude. Neutrinos double beta decay is a fairly complex process, right? There are people who have spent decades studying this, actually, literally, and there is a bunch of different mechanisms besides just the standard light neutrino exchange that can contribute to neutrinos double beta decay. So I would say that it's actually a great probe of new physics, really, right? So, and what it probes really is lepton number violation. So it's not just about, I would say, excluding inverted ordering, right? I think it would be much bigger discovery. We saw this process because that would be really new physics, and somebody would be surely flying to Stockholm. However, to unravel the underlying new physics just with double beta decay would be really challenging. So I think it still makes sense to look for lepton number violation elsewhere, and to make it easier for people to get constraints from lepton number violation or from neutrinos double beta decay, we have developed this tool that is available online that you can use. And we have also looked into lepton number violation at colliders. So what's next? The outlook maybe look into the simplified models where the EFT can be also used as a kind of guiding principle, because you can take now these effective operators, can open them up, and you can think about all the possible UV completions that they may have, right? And then you can take advantage of that, and you can take advantage of the resonant production of these particles, maybe at colliders or elsewhere, and compare that with the EFT. or you can also go beyond standard model EFT, and you can consider, for instance, that one stellar neutrino is lighter, so you need to include it in the EFT, and that also changes then the picture quite a bit. Okay, so I'd like to thank you, and before the questions, to shamelessly advertise this workshop. So in case you enjoyed Florence, but you're tired of it, and you're tired of Chianti and Aperol, maybe you want to grab proper half a liter of beer in Prague in September. So I think, and here, of course, something about neutrino physics too. So that's astroneutrino theory workshop that we'll be organizing in second half of September. Is one of them. So I think will be. Yeah, thank you.
Thank you very much, Lucas, for this enlightening talk. So, for Lucas. Yeah.
Could you comment on the mu minus goes to E plus process? I still don't know which diagram. It's actually, especially I'm curious about whether it's how it's sensitive to Majorana.
Many backup slides somewhere. Is here, right? So yeah, it looks actually like, again, like neutrinos double beta decay, right? Just now you flip this one like, and you start with neon, right? And yeah, okay, this is the contribution of some higher dimensional operator, but if you just ignore this, if you just insert here, sorry, you just insert here the neutrino math, then yeah, that would be the process.
Yeah, about 10 TeV is a 1 TeV or 10 TeV? Is it?
I'm sorry.
1 TeV is about the scale we can probe.
Well, yeah, but with this, yeah, right, yeah, which is quite beyond. It's 7 orders magnitude.
Beyond how much you can probe? Like
I'm sorry.
For dimension 5.
This is for dimension 7, but you can, yeah, of course, like any source of Lepton number violation would contribute to that, and maybe within, yeah, that's another thing, within like specific models. Typically, if you generate higher dimensional operators, if you take like heavy fields, you take, for instance, heavy right-handed neutrino exchange here, the rate improves. So yeah.
More questions for, yeah.
I have a question again on the compilation you did. So I saw you chose 127 for the value of the axial vector coupling constant in the compilation that you did for the neutrino-less double decay half-life.
For the constraint?
Yeah.
Yes.
So you in the table with the different values of the couplings, you fixed GA to 127. Voila, that one.
I think you mean this plot at the beginning.
No,
very beginning here.
No.
This
with the models.
Yeah. Here we have GA.
GA.
Yeah.
Okay.
27 and case, yeah.
Okay,
in some models they talk about quenching.
No, because there is a quenching, and the quenching is a delicate issue. So I would like to know how. I mean, I know that many of the available calculations took 127, but so what did you do in your compilation?
Oh, well, yeah, you can take any GA that you like, right? But I think the recent progress showing that the quenching is actually not there. It's more like a systematic error introduced by these phenomenological models. So then the question is, yeah, how well you understand your model, like you're able to estimate these systematics maybe, and
yeah, but since
because the GA, the whole nucleometric one is proportional to that, right? Because you can express also the other form factors, maybe in terms of GA, and then you can play with that. So here we were showing it only because at the time people were this, and yeah, some people were calculating the limits with J equals 1. Some people were just taking the usual 1.27. And so,
yeah, but we know from other observables that there is a quenching, and then the original quenching, okay, in the allowed has been sort of solved, but the value of GA depends on the specific model you are considering. So if you dissociate the value of GA from the value from the model you are considering, there is
I mean,
sort
the
of,
clear structure model.
yeah,
Yeah,
I mean,
yeah, but-
it's
but in-
related to the,
yeah, but in
for
this-
example, a correlation.
Yeah, in
Yeah,
phenomenological model, so here we were using the IBM, right? Yeah, there is no really handle on that. There is no kind of renormalization going on. So I think that's what the ab initio people claim that they can do. Yeah, I've seen even some error bars. Yeah.
Yeah,
whether
but the
they're
models you
trustworthy.
considered
yeah.
are not these ones, no, they are not.
No,
initio.
this is,
These
this
are
was,
old models. I mean,
this was, yeah, more phonological, this was
Yeah,
algebraic.
yeah, yeah.
Advantage of that was that actually with that is a simpler calculation, and you're able to calculate the matrix elements for a variety of different isotopes, right? So
Yeah.
so then you can
Simpler,
play with
I
that.
don't know
yeah.
what do you
I mean, it
mean.
doesn't take as long as
It's a
Shell
very
model calculations. yeah.
calculations. are
It's
not
an
that
approximation to Shell model, right? So-
Okay, not only, but, and the other question I had in
Mhm.
your choice of matrix elements, because the calculation spans over decades, as you,
Mhm.
and some are very old, some are more recent, some
Mhm.
test calculations, some fix, for example, some of the coupling constants on the two neutrino, I
Mhm.
mean, use constraints from other
That's true,
observables.
yeah.
So they are not all of the same quality. So how do you pick that?
Yeah.
Did you apply selection?
No. Well, usually people show everything. Yeah.
Everything is not necessarily the same. I mean, now I'm a bit.
Okay.
I mean, I know that people take the method. I mean, but
Yeah.
one has to know
Yeah.
what's in the model,
it's-
how the
it's true.
calculations are
Yeah.
done, but showing everything is not maybe the right thing.
Yeah, maybe the reason for that is partially that what do I? No, too many slides. Where are we here? Yeah, maybe partially the reason is that really the more modern sub initial calculations predict smaller values, right? So it's negative result in a sense, right? I mean, it is what it is, of course, but yeah, then it suppresses the rate even further. So the constraint doesn't look as great. So maybe that's why people prefer to show still some of the older calculations. Yeah, that's another thing. Yeah, that they so far. Although I think I've seen, yeah, I think the China people can already do even like Xenon 136, or they claim so at least. There was a paper last year, I think. Yeah, and they even ran it for they have many parameters in the model, right? And so they can do even kind of a statistical analysis of that. So they actually have some error bars for their model. So yeah, there has been some progress. So maybe that's yeah what should be really used. On the other hand, so they are smaller, but there is also there are some of these additional contributions. There was a paper by Vincenzo and Cirigliano, and so that was mentioned last week, I think, and talked by Federica. Yeah, so that helps you on because the associated low energy constant, it comes with a positive sign. I think that's already quite clear, and it is not negligible simply, and it's going to improve then, let's say, and can take you back a bit higher. The combined matrix element is again a bit large, right? So then it's like yeah, it sounds almost like an even number of mistakes, right? Maybe was done by but then again, like the people who are working on, I don't know, QRPA or so, they claim, well, but this contact term is actually there, like we have this short range correlation there. So
Yeah, sure.
So congratulations for the work. So my question is basically concerning somehow the fact that this is a rare process and we are making it's difficult to proceed, no?
Yeah.
Now, I think that the question of time is particularly severe for experimentalists. I mean, they spend entire life. For us theorists, things are easier to a certain sense,
unless
but
you are
probably it's not that easier if we try to be useful and to do something somehow valuable for progress. So my question is indeed an assessment on this, especially the particle physics side, that it is the one that you presented.
Yeah.
So somehow whether you have, what is your view on the way to proceed? I mean, what could be most useful to do next? Of course, any of us does.
would be to observe neutrinos double Italy.
Yeah, but we theorists probably won't be able to do that. I mean, we probably could do something
No,
else.
I would say that like the theory is like actually, yeah, it has been improved quite a bit over the last decade or so, and that most of the things are I would say almost there, or like but there is maybe yeah, you can, of course you can think about like some more exotic contributions and some specific things and so on, and motivate maybe to experiment further. But yeah, it would be nice, for instance, for these non-standard contributions to know these low energy constants, but yeah, I don't think that, yeah, that's very costly to calculate those, right? Like what these calculations are not cheap, and also they take a long time. So I was talking to one of the lattice people, and he told me, so Lucas, would you spend your next 10 years on calculating these without observation of the process? So I was like, of course. but
Most frankly, I guess that standard model language suggests that this, say, contribution connected to mass is the most somehow plausible.
Yeah, I think
Now,
that
but how to proceed on that? This is also a question. I mean, we at the moment we are stuck. I mean, we are realizing that we exploit say oscillations and cosmology now.
Yeah.
But we are there. I mean, there is no effort in that direction.
Is quite accurately calculated. That's quite under control. So yeah, I think now that's the task is for the experimentalists. Yeah.
So the one step was just determine mass hierarchy. I think that's important. And then maybe to see what cosmologists tell us, at least in this double bit decay story. Hierarchy, which could be determined already 10 years ago, just because we didn't insist it in right way. Where Pingo is, for instance. There is no Pingo, so just Orca. Why Orca is so slow? There is no money. Oh, better to spend money on Dune and not on Orca, just to produce more photomultipliers.
I guess so.
I absolutely agree. I mean, especially on things that we can control, like say MSW effect being clearly exploited. Yeah, which is not done. I agree.
Yeah. Cosmology is currently showing 3 sigma tension with inverted hierarchy with the latest measurements, cosmological measurements. So, but it also shows a 2 with the normal one. So, yeah. I mean, DESI now sets a limit of 4.72 eV on the total neutrino mass. Yeah. So we found a stronger limit, and we are finishing a study in which we find from our stronger limit that we find that is 0.041 or 42 eV. We find a 2 to 3 sigma tension between cosmology and neutrino oscillation experiments for the normal hierarchy. And for the inverted one, the tension is between 3 and 5 sigma. So, I mean.
Or indication that neutrino masses have dynamic origin.
Yeah, sure. Yeah, of course, time varying masses. Yes. I completely agree. I mean, if we keep going this way, to change the cosmological model is not gonna be enough. You know, I mean, we need to change neutrino physics, probably going to non-standard models, or if you want to more exotic things, non-standard. From my point of view, I would say better to change the neutrino sector, that is the one that is giving us surprises somehow, than to change the gravitational one. I mean, this is something. Okay.
There are also tensions, right?
Yeah.
And then one does see them, so maybe.
Yeah.
Maybe that is also.
Yeah.
But I think these are independent.
But
independent measurements.
But
we should just continue with everything. And I think experimentalists are also making progress. I think these germanium detectors are very high energy resolution. So the claims are that they would need just one event, and they would see it. Right?
I have another comment or question for you.
Mm-hmm.
I mean, you have this beautiful software thing, right?
Yes.
In which this Python tool in which you compute, right? You have what why don't you add another, let's say, section to this in which you add also, you can do some forecast for future neutrino double beta decay experiments and some, some sensitivity curves and such? You are not considering to doing that?
Well, this in principle you can do that because you can put in like, okay, so some bounds from the latest results from experiments are incorporated, right? Of course, but this half-life, this bound you can put
So
it by
you
hand.
can
So
do it, right? Yeah.
we want
Yeah.
10 to the 28 years, you can
Yeah.
do this. So
Okay.
that's
Okay.
yeah, the
Okay.
tool can do. It gives you even the formula, right? So and then
Okay.
you can take the formula, I don't know, to Mathematica or anywhere, and you can
Okay.
play with it,
Okay.
whatever you're used to. Yeah.
Okay. More questions for our speaker? If not, let's thank Lucas again.